Welcome back. In this video, we're going to review what we've learned about the atmosphere and relate the barometric pressure or the atmospheric pressure to partial pressure of a gas. So when we talked about the atmosphere before, we said to imagine that you've got a column of air that goes up from the surface of the earth all the way up to the edge of the atmosphere. And we know that pressure is the force that's applied per unit area. And so the pressure that's at the surface of the earth is in part due to the weight of that column of gases. And if we go up in elevation, then the density of gas is going to decrease, as well as the pressure. And the reason for this is because there are fewer molecules up above that point. So again, if we're looking at this vertical column of air, and if you go up an elevation halfway to the top, then all of a sudden you've lost a large portion of your molecules. And it turns out it's more than half of them, because the majority of the molecules, the gas molecules, are held closer to the earth. So therefore, at the higher altitudes, we have a lower pressure. There's simply fewer gas particles that are pushing down. And we can see this if we take a look at the pressure as a function of altitude, then it decreases drastically. When we look at the collision frequency, this is another way of describing the pressure. So at the surface of the earth, there is a very, very, very high collision frequency, but that collision frequency drops again dramatically as the altitude increases. And so since pressure is proportional to the collision frequency, as the altitude increases, our pressure goes down and the number of collisions also goes down. When we talk about the barometric pressure, this is the measured pressure of the atmosphere. So at sea level, the barometric pressure is 1 atmosphere, barring any extreme weather conditions. If we go up to 50 kilometers above the surface of the earth, the atmospheric pressure, the barometric pressure, is about 10 to the minus 3 atmospheres. The atmosphere is made up of a variety of different gases, and the exact composition of the air at any given moment is going to be a function of the weather, a function of your geographical location, what pollutants are being put into the air, how it's being filtered out, etc. But for the most part, if we take a look at dry air at sea level, so that we've removed all of the water from the air, then we can see that it's about 78% nitrogen and 21% oxygen. And so those make up together about 99% of the atmosphere. There's a very small proportion of the other gases, of argon and carbon dioxide, methane, etc. Because for those gases, there's a very small proportion. Instead of talking about the percent that they occupy, we will tend to use the units of concentration of parts per million, parts per billion, or even parts per trillion. So parts per million, billion, and trillion is calculated by taking the mole fraction of a gas and then multiplying it by either a million, billion, or trillion. So it's equivalent of saying how many molecules of that gas there are, or how many atoms of that gas there are, if it's a single atomic gas like argon or neon or helium, per 1 million molecules, or per 1 billion, or per 1 trillion molecules. So let's do a couple practice problems here. So you're given the composition of the atmosphere on top of Mount Nittany, which is in State College. We see that it is about 78% nitrogen, 21% oxygen, and then a very small fraction is argon and carbon dioxide. So for this first question, we want to determine the partial pressure of oxygen when the barometric pressure is 725 torr. I'd like you to pause the video and try this on your own, and then I'll walk you through a solution. Welcome back. So if we want to find the partial pressure, what we need to do is we need to determine or relate the mole fraction to the total pressure. remember that the barometric pressure is the total atmospheric pressure. So in this case, our barometric pressure of 725 torr is our total pressure. Our mole fraction is the 0.20946. So that gives us then a partial pressure of oxygen of 151.9 torr. And we could be done here. However, if we wanted to convert this to atmospheres, then we would need to use the conversion between atmospheres and torrs, and we'd see that this is about 1/5 of an atmosphere of pressure. Here's a second problem. What would be the concentration of carbon dioxide in parts per million? Pause the video and try this one on your own. Welcome back. So to determine the concentration in parts per million, we need to multiply the mole fraction by a million. Our mole fraction is 0.00039,445. Multiply that by a million, and we get 394.45 parts per million. What that means is that for every 1 million molecules of gas, there's about 394 which are carbon dioxide. And if we wanted to relate this to the partial pressure of carbon dioxide, we can multiply the mole fraction by the total, and we get 0.286 torr. So as we would expect, because the proportion of molecules of carbon dioxide is very small, only 394 per million, the pressure that they contribute to the atmosphere is also very small. That's it for this video. Thanks for watching and have a great day.